So up until now, we've had essentially at least one reactant that we've had unlimited or truly in excess. We haven't really cared about having specific quantities of each of the elements, or each of the compounds. We've looked at how many moles it would take minimum to make a reaction happen. But now we need to look at what if we only have a certain amount of starting material, how much product will we get? So the question is, what happens if we don't have an unlimited amount of a certain reactant? Discuss in your group and see what you guys come up with. It's a pretty simple answer. Really, one reactant will run out first. We're going to use up all of one reactant and we'll have leftovers of another. The question is, how do we know which reactant is going to run out first? It's not necessarily the one with the highest number of moles. See if your group can come up with what else might determine which reactant is going to run out first. You have to look at the mole ratios. So you need to look at those coefficients. What's the ratio between the two reactants? That's what's going to determine which one runs out first. And it's also going to determine how much product you're going to be able to make. So let's look at an example. So we're going to step back and we're going to look at molecules again. Remember, we can easily go between molecules and moles. Moles is simply 6.02 times 10 to the 23rd molecules, so we're just scaling it down so we can actually draw particle diagrams. So suppose you have 4 molecules of hydrogen gas, and that reacts with 4 molecules of oxygen gas, and you form water. So if we were to draw a particle diagram of this, we'd have our 4 hydrogen molecules, so it's H2, they come in pairs. I showed them with squares, and there are 4 of them total. So I have 8 hydrogen individual atoms. Same with oxygen, it comes in pairs, it's O2. I use circles to show oxygen, and so we have 4 pairs because we have 4 molecules of O2. Question is, how much water do we make? So we know that for every 2 hydrogens, you need 1 oxygen. So if we have 2 hydrogens, we use 1 oxygen. So 2 hydrogens and an oxygen. We still have more. Let's keep making them. 2 hydrogens and an oxygen. 2 hydrogens and an oxygen. 2 hydrogens and an oxygen. So we've now used up all of our hydrogens, but we have leftover oxygens. So if we were to answer these follow-up questions, how many molecules of water do we make? 1, 2, 3, 4. Which reactant is in excess? That means which one do you have left over? You have oxygen left over. And how many leftover molecules do we have? We have 1, 2 leftover molecules. There has to be an easier way than just drawing particle diagrams. And there is. So if we use our BCA table, we have to write our balanced reaction first. So H2 plus O2 gives you H2O. We know that we need a 2 here and a 2 here to make it balanced. Just like when we drew particle diagrams, we could bounce back and forth between moles and molecules, we can do the same thing here. I could say that these are 4 moles, I could say that they're 4 molecules. It's a matter of scale. So if I add all of my units, and we look at our numbers, we'll probably see that we have some things in common with our particle diagrams. So we had 4 and 4 and 0 to start with. We don't start with any water. We used up all of our hydrogen, so we're left with 0. We used up half the amount of oxygen. 4 divided by 2 is 2. So we have 2 left over, and we made 4 waters, and so we have 4 moles of water here. So how many moles or molecules or moles of water? We made 4. Which reactant is in excess? And this after which reactant, remember this is our reactant side, which one did we have leftovers? we had leftovers in the oxygen. And then how many leftover molecules or moles? We had 2. So if you look back in those in your notes, those are the same answers we got from drawing the particle diagrams. So what determines how much product can be made? Discuss in your group, see what you guys come up with. It all comes back to that mole ratio, the ratio between the reactants and the ratio between the products. We can't make more waters because we ran out of hydrogens, even though we had leftover oxygen. We would have had to add more hydrogen. Our hydrogen then is our limiting reactant. Called the limiting reactant because it limits how much product can be made. It's the one that runs out first. So do you think we always need to draw particle diagrams? Which one of those was easier, drawing the particle diagrams or using the BCA table? Some of you might say particle diagrams, but really it's going to become faster to use the BCA tables and just look at the numbers instead of drawing particle diagrams for everything. So let's look at an example where we don't use particle diagrams. If you have 6 moles of nitrogen gas and 12 moles of hydrogen gas, how much ammonia will you produce, NH3? So we have N2 plus H2 gives you NH3. We know that this balance is 1, 3, 2. We fill in our BCA table. We have 6 moles to begin with, 6 moles of N2, 12 moles of H2, and we know that we have no NH3. But if we're not going to draw particle diagrams, we need to figure out which one of these is going to run out. So we're going to have 2 options, and we're going to work through this twice. So option 1, the first scenario, would be that we'd use all of our nitrogen gas. So when we set up our BCA tables, this is the same reaction, same numbers, we'd run out of our nitrogen gas and have none of that left over. Option 2 would be to use all of our hydrogen gas. Same reaction, same balancing, same numbers, but this time this is what we're running out of. So work through it in your groups, and then let's come back and check our answers. So if we're looking at the N2, or if we're looking at option 1 where we use all of our nitrogen gas, we use 3 times as much hydrogen gas as we use nitrogen. 3 times 6 is 18. So we'd use up 18 moles, we'd need 18 moles of hydrogen to react with our 6 moles of nitrogen. And then we'd produce twice as much NH3 as we would use N2. So we would gain 12 moles. So our after would be 12. And, well, 12 minus 18, that gives us minus 6. Can we have minus 6 moles? Can you have minus 6 of a molecule or something like that? We have a problem here. We can't have negative amounts. So let's examine option 2. So here we used up all of our H2, our hydrogen gas. So we're left with 0 here. We know that we use 1/3 the amount of hydrogen for our nitrogen. 1/3 of hydrogen is 4. So we'd use 4 moles of N2. That would leave us with 2 moles left over. And we know that we'd make twice as much NH3 as we'd make, or as we'd use of the nitrogen gas. So 2 times 4 is 8 moles. So we know that we'd have 8 down here. Now, we have no negative numbers, we have leftovers. We ran out of the hydrogen gas and we had nitrogen left over because we need 3 times as much hydrogen as we have nitrogen. And we produce twice as much NH3 as we would use N2. Or you could say we'd use 2/3, or we'd produce 2/3 as much NH3 as we used H2. Either of those would get you 8. So our question asked how much NH3 would we produce? Well, we know we have 2 different answers. We have 12 here and we have 8 here. Question is, which one's right? Your gut should be telling you that 8 moles is the correct answer. In this scenario where we produce 12, we were actually in the negative values. We could produce 12 if we had 6 more moles of H2, then that would work. But we're in the negatives over here, and we can't have that. We can have leftovers, but we can't be lacking. So that's how you would work through a problem without drawing the particle diagrams.